Come aboard, bring along all your hopes and dreams. As long as Leo's here, we'll do it great. Okay, so here's a concave mirror example. We've got a 1 centimeter high object placed 10 centimeters away from a concave spherical mirror whose radius of curvature, C, is 30 centimeters. We're going to draw a ray diagram to approximately solve this just real quick, and then we're going to determine the position and magnification using our mirror lens equation and our magnification equation. So if we just want to draw a picture here, hopefully what we first recognize is that if our object is 10 centimeters here and the radius of curvature C is 30, that means our focal length is 15 centimeters here, which means that this object has to be inside the focal length. It's closer to the mirror than the focal length is. And because of this, when we go ahead to draw our ray diagrams, this is what we're going to see. We're going to have a ray that, comes straight, hits the mirror, and then it's going to pass through the focal point. Perfectly done. That is not even close. Closer, I guess. Good enough. The second ray that we draw is supposed to pass through the focal point and then hit the mirror, but that doesn't work. So how can we do this? Two other lines that we could draw. I like to just draw one that's going to strike the center of the mirror, the plane surface of it, and when it strikes, angle of incidence and angle of reflection will be the same, so it will come out at the same angle it went in, and it'll do that. And notice when we do this, these lines, they don't look like they're going to hit. In fact, they look like they are diverging, which is that's a boo-boo. If you want to draw this line instead, you could actually draw a line that goes, these are the lines you draw. These are the lines that, they're the easiest ones to draw, okay? Because you can mess these points up, so we'll stick with these two. But these lines are diverging here, so what we actually need to do is we need to backtrack these lines. So let's take this straight line here for the orange, and we're going to backtrack it onto the other side. Does that look decent? I'm going to twist my head. That looks terrible. That looks anti-bueno. There, I think that looks better. That looks a little better. And then we're going to backtrack the green line as well. Backtrack. That looks pretty good. And when we do this, we see that these lines actually intersect here. Now, remember, on this side, there is no light over here. There's no actual light. But our eye is perceiving there to be some light over here. These rays, it thinks, have to come from somewhere, so it's generating them in the back. And what your eye sees visually is this. It generates the image out here. This is an upright image because it hasn't flipped, which means it's immediately virtual. It's immediately a virtual image. We also know because it's upright that the magnification for this better be positive, okay? Because we have not flipped. And if we just take a look at this, our image became larger than the object, so this magnification better be greater than 1 whenever we saw it. So let's actually figure out what the magnification of this object is, and where its position actually is from the mirror. So let's work this into our equations. So let's first just try to figure out if we wanted to get a magnification, then we need the image height and the object height. So this is the object height here. We don't know the image height. So, oops, I didn't mean to write that DI. That's HI. We don't know the image height, but we do know the object height. That's kind of nice. But because of that, we can't immediately just say what the magnification is. We need a way to relate this to something. And if we recall in our magnification equation, we know that we can say that the image height over the object height is equal to the negative image distance over the object distance. So let's try to find our image distance here in order to get this to all work out. So to find the image distance, we can go and use our lens equation, or our mirror equation, however you want to call it. 1 over f equals 1 over di, what we're looking for, plus 1 over do. And, well, we know do in this case. DO is going to be equal to 10 centimeters. So let's just call this 0.1, right? And we know F. We know F is half the center of curvature, which is 0.15 or 15 centimeters. So we can say here that this equation is going to become 1 over 0.15 equals 1 over di plus 1 over 0.1. Now, if you wanted to, you could actually leave this as 15 and 10 and keep everything in centimeters if you wanted to. There's nothing wrong in that. Just your di will be in centimeters instead of meters. So just be careful, okay? If we solve for di here, got to do a little bit of math. First, we're going to subtract 1 over 0.1 to the other side. So we're going to have 1 over 0.15 minus 1 over 0.1. This is going to equal 1 over di. And then when we actually solve this, you need to be very careful. It's very common for students to mess up this kind of algebra. It's best if you do 1 over 0.15 first, and then do 1 over 0.1, and then subtract those numbers. So when I do this, what I'm going to get is 1 over 0.15 is 6.66, repeating, of course, minus, and then 1 divided by 0.1 will give us a easy 10, and that's equal to 1 over di. Okay? Now, why does this matter? Well, when we do this, 6.666 repeating minus 10 is going to give me negative 3.3 repeating. That's equal to 1 over di. Now I need to flip this, so 1 divided by the 3.3 repeating is going to equal to di, because I need to take reciprocals of each side. So 1 divided by 3.333 repeating gives me di. Well, this is a negative, and we find that di is going to equal to negative 0.3, okay? Which means that it's at 30 centimeters or 0.3 meters. Now, if you're looking at this, you might be thinking to yourself like, whoa, time out, Mr. Botzer. How did you get a negative distance? That's a bunch of nonsense. You just pulled that out of nowhere. Well, it's a negative distance by convention. There's a lot of convention that goes into geometric optics. And this is by convention because this is behind the mirror. Okay? Remember, while that di is 0.3, you know, it's all the way over here, there's actually no light over here. The image isn't actually here. It doesn't exist. It's virtual. So when it's behind the mirror, by convention, we call these negative distances. And this will actually really help us because when we go to use the magnification equation now, what we're going to have is that the magnification is going to equal negative of negative 0.3 divided by 0.1. And when we do this, we find, well, the negative of my negative is a positive, and 0.3 over 0.1 gives me 3. So we see that our magnification here is 3, so it is a value that is larger than 1. Our image is 3 times larger than our object, so it should be 3 centimeters because our initial object is 1 centimeter. And notice that because we're upright and virtual, by convention, that magnification is positive, which it is, because the negative of my negative virtual distance gave me a positive back. Okay, so that's one tiny thing we have to be careful about there. For mirrors, anytime our image is behind the mirror where there's actually no light, we actually have negative image distances in that case. So you want to be careful about that. It's a little bit of a weird thing.